Hello, everyone. Thanks for coming in. So we're going to be talking about porting Apache Sqoop on Apache Spark. So we'll just do a quick intro and then get into the talk. So I'm Veena. I currently work at Uber. Mostly people are here because of that, I guess. I don't know. So I work at streaming systems here at Uber, and prior to that, I worked at Cloudera for a brief period. That's where I actually got into understanding the data ingestion part of the Hadoop system. And before doing that, I was working in a very different domain in service and front-end infrastructure at LinkedIn.
Hey, can you hear me? Hey, I'm Vinod, and I'm an engineer on the Hadoop team at Uber. So I'm now at Uber focused on building a real-time pipeline to get data into our Hadoop clusters. And before this, I was at LinkedIn working on a distributed key value store called Voldemort, which is like Cassandra, I guess. And then before that, I worked at Oracle for their log-based replication products, and grad school did a bunch of work around stream processing and high-performance computing. And so I've basically done data for a long time now.
OK, so we're just going to switch back and forth and go with the talk. So we've kept our agenda really simple so that we didn't want to bore you and put in too much information. Our agenda is seriously simple. We'll talk about what data ingestion is today and what it means for us, especially working in companies like LinkedIn and Uber, what data ingestion has evolved to. How many here, by show of hands, know Apache Sqoop? So there's a decent amount of people who have used Apache Sqoop. Frankly, I didn't know much about it until last year, so I'm very honest about it. I'm going to here talk about some of the evolution of the Sqoop that came out early on in 2006. That's called Sqoop 2. Lack of better name, they just call it Sqoop 2. And then later on, I think Vinod is going to spend a little bit of time on how we did a POC on porting the Sqoop ingestion tool on Apache Spark and why it's useful to us. Lastly, some insights and what we want to do next with this project. So this is in the beginning, right? When we all started with the big data ecosystem in Hadoop, our primary requirement was basically transferring data from SQL-like sources to Hadoop. So here are some examples. Sorry for my scrappy diagrams, but I think you all understand what that is. Most of the use cases initially were just transferring data from SQL or Postgres or some legacy SQL-like databases into Hadoop. Recently, I think primarily in the beginning, it was HDFS support. You were able to move data from SQL to HDFS in plain text or sequence. They've also added support for moving stuff into Hive and HBase. So that's all I know about Sqoop 1, and nothing more, frankly. So for a long time, Sqoop solved, and I think a lot of people, I worked at Cloudera for a brief period, and I knew that a lot of customers used it. So Sqoop did solve the basic problem of transporting data between SQL and Hadoop. But what's really happened is the concept of ingestion has evolved over time. It's no longer SQL to Hadoop. We have a lot of sources that are non-SQL-like. For instance, companies like I worked at used non-SQL sources, and like Cassandra or Mongo maybe, or Redis, and they want to move that data out onto Hadoop at some point. There are a lot of messaging systems, and I come from a company that kind of built Kafka, and we use that for pipelining and transferring data across multiple channels. So that also acts like a data source. And recently, we've also seen that it's not just like SQL to Hadoop, but there's multiple stages of ingestion pipelines that could happen in a typical a large company or an enterprise company. So Sqoop 2 actually is a name given to the evolution of Sqoop. It's built on top of Sqoop, but it's quite different, though. So instead of just keeping it from SQL to HDFS or SQL to Hadoop, they've kind of made it really generic. And that was a neat move, I think. So you can actually move data around from any source to any source. So that's the gist of it. That is, you could get data from MySQL and put it in Kafka. If you have an FTP source for files, you can use that and then put that data into HDFS. If you are using non-SQL-like stores like Cassandra, you can also use that and then put it into Hive. So it's just become a very generic infrastructure tool. How it does that is you can actually write these pluggable data sources. We'll go into that in a bit detail later on. And Sqoop 2 is a little bit more fancier than Sqoop 1. It's a server client architecture, so there are a lot of tools supported for you to actually create these jobs that do ingestion and writing into data sources. So two things, if you have to kind of understand why we thought about doing this on Apache Spark, I think we have to give you a little bit of background on Sqoop 2. Hopefully I'll keep this short, but you have to understand this one concept of Sqoop 2 called connectors, which is not very unique. I think tons of systems have done this. There's nothing fancy about it. So connectors basically allow you to give that feature of pluggable data sources. Second thing is obviously every single thing runs as a job in Sqoop, so you have to understand how you create that, and you need that background to understand how we did Sqoop on Spark. So again, short story of connectors, they represent data sources. Don't mean by sources mean they can't be data sources that you write to. It's either or. It could be sources where you read from, and then sources also that you write to. So these are common examples that we deal with in and out, and there are some connectors already for Sqoop 2 to represent some of these, if not all of these data sources. So important thing to understand basically is how are these connectors expressing themselves, right? So connectors are representing data sources, but data sources have properties. So for instance, if you take JDBC, if I want to connect to JDBC, you need to kind of tell how to connect to it. If you want to connect to Kafka, so you need to know the zookeeper host and the broker host. So these are all properties of data sources. And again, this is no brainer. One of the ways we do this is through configs. So there are specific kind of configs every connector exposes. And that is very done in a generic way, so you can add as many kind of configs you want. There is no tying to Sqoop. So when you write a connector, say, for some data source, you have the full flexibility of coming up with your own set of configs. But primarily, you have to do two things. You have to provide a config that somebody might be able to fill in and say, oh, this is how you connect to me, and that's called a link config. Here's an example where if you create a JDBC link object, you would have to fill in the driver, the username, password to connect to it. Similarly, once you've done with knowing how to connect to a data source, you also may want to know more information of, example, what table in that data source you want to read data from or write to. In case of Kafka, it could be a topic name that you want to know. You want to probably know what's the schema associated with that topic. So these are the attributes of a job. One really important thing you have to remember is basically, these jobs reuse the link configs. Multiple jobs reuse the link configs, but every job is unique in its way with its job config. So once we're clear on what the connector is and how they express themselves, we come to the second part of if you were to ever write a connector for Sqoop 2, hopefully you will, these are the APIs you have to implement. We'll go over in later slides why these are important. Usually the concept of Sqoop is you're able to extract data from one source and write it to another source, as simple as that. So you have to provide us means of how you extract data from your source. No one else but the connector knows about it. Similarly, you have to tell us how you're going to load data into your data source. So, and then the third thing that may not be obvious is usually when you want to run in a high-performing environment, it's usually good to kind of implement the partition API that also Sqoop 2 provides in the connector that allows you to distribute your extraction equally or parallelly across multiple nodes. So once you're done with these three things, you end up writing your first connector. So your first connector could basically be written in a few hours, as long as you implement these APIs and expose the configs you want to expose. So once you know about connectors, you have to understand what a Sqoop job is. These are the three things that we will go over again in detail when we talk about Sqoop on Spark. But primarily, once you have understood connectors there are a lot of inbuilt connectors Sqoop 2 comes with, but you can also contribute some. You're going to use those connectors and actually run a Sqoop job. So a Sqoop job is it's a job that will basically get data from source and write it to a to source. So let's look at these three things a bit before I hand it over to Vinod. Let's take a concrete example, right? And maybe I'm rehashing the same thing. You know MySQL, and then you know Kafka, I assume. So these are two sources that I want to get data from and data to. So first thing you want to do when you're creating a job is you want to create the link objects. One nice thing about Sqoop 2 is it has its own meta store, like in a way. So it stores these link and job objects you've created. But if you're bootstrapping your system for the first time, you have to kind of initially create these objects. So let's say my goal today is just to get data from MySQL and then put it into Kafka. I will end up creating 2 link objects. As I've already explained, you have database rows, and then you have messages in Kafka. To read the rows, you probably need to connect to it with certain JDBC properties. So you're going to create a link object saying that. Similarly, you're going to create a link object for Kafka, telling what the ZK host, the Zookeeper host is, or the Kafka broker list is. So once this is done, you pretty much kind of created your first step towards a job creation. So a job in Sqoop, in one single sentence, is an association of a from connector to the to connector. That means every job uniquely identifies what is the from data source and the to data source. So once you have gotten the link objects in place, you can start creating as many jobs as you want. Why do I say as many jobs? Because every job is unique in its way on which table it's importing from and which topic it's writing to. But it can reuse those link objects. So this is pretty much the gist of it. So in our case, the table name, the partition column, it could be a free-form SQL query. These are kind of job configs you have to populate while creating a job. And similarly for the to, in case of our case, it's Kafka, right? So I have to tell what's the topic name. Probably I have to tell what is the format I want to encode the messages. Is it Avro or JSON or freeform? Those are some of the configs. Again, all of these are up to the flexibility of the people who write the Kafka connector to make it as a config and then expose those to the Sqoop job creator. So this is just an example I've given here. So in code, typical Java or Scala, whatever you want to do, you basically end up writing simple 4 to 5 lines of code that ends up creating a job object and persists it. So I'm not going to go in detail, but I think this is just for reference on how you're going to create a link object and a job object. The nice, interesting part of this is, the second interesting part of job is once you've created these job objects in Sqoop, they're there in the repository. You can actually look them up. Their REST API is exposed. You can understand what the properties are. The second thing is job submit. Since Sqoop came about during the time of Hadoop, they kind of leveraged the MapReduce execution and the submission engine a lot to achieve the parallelism you need. So today, as if you're going to go run a Sqoop job on Apache Sqoop 2, it's going to use the MR client to actually submit the job. And all of these configs that I was talking of, like the link config and the job configs that are required in the Sqoop job are kind of exposed into the MR using the Hadoop configuration object. So if you understand these things, you pretty much know what happens rest, right? So if you're familiar with MapReduce, and I hope lots of people here are, we're going to tie the connector API with the execution now. That's the third part I think you should be familiar. So if you remember, I talked about connectors, right? When you talked about connectors, you said you have to implement these 3 APIs. And if you're wondering why and how those APIs get used, this is how. So this is the slide that connects it all together, right? So the job execution in Sqoop 2 primarily relies on the MapReduce engine. So there are 4 things that they use from the Hadoop world. First thing is you have to parallelize this. The basic problem we're solving in Sqoop is extraction and loading. And you want to do it in the most performant way. That means you're able to leverage Hadoop MapReduce engine for parallelizing it. So you use the input format and the splits to determine what are the number of partitions that particular connector can expose. Finally, you use the mappers to actually run the extraction. So you may have n number of mappers. So that is also a configuration you can give in the job saying, to load data from MySQL, I want to create 20 mappers. And then to write data into Kafka, which is my to source, I might say I just want 4 reducers. And the 4 reasons, the reason I would say 4 is basically maybe I have 4 partitions in that particular topic, and I want to just have one-to-one a writer associated with it. So these are the 4 things you use. And finally, obviously people know the output format in Hadoop. We use that to finally commit that or abort a job if something went wrong in the execution. So this is in gist how Sqoop 2 currently works. And this is the part that I learned when I worked at Cloudera, right? So if everything is so good, why are we here, and what is that we're actually talking about, right? So what's a Sqoop about? So the Sqoop here is that it turns out even in Sqoop 2, the execution engine could be plugged in. Like it was designed in a way that it doesn't really have to run on MapReduce. The simple job of transferring data from a source to another source can be done in many different ways. So we explored, we both talked about it, and we said, why don't we just replace a MapReduce with a new cool thing that's out there, which is called Apache Spark. And it gives you the same parallelism. And also, we've been basically talking about extract and load until then, right? Until now. So we could also explore, with the variety of operators Apache Spark supports, transformations in between the extract and the load process. And I'll turn now over to Vinod, who's going to take over and explain why we chose Apache Spark and how we've implemented this.
Thanks, Veena. So the question really is, why not? Because a lot of companies already use Spark for expressing their ETL jobs and their data transformations that they want to do. And like in general, right? Okay. So, and we all know of that for most workloads, I think Spark is kind of faster than MapReduce on a lot of workloads. And then there's a growing community embracing Spark. So if you're already using Spark for a lot of your things, which is the case for us, you know, in some cases, there's a Spark infrastructure which is available. Maybe you don't have the infrastructure to run MapReduce. Say, for example, you have Mesos in a data center, but you don't have, like, say, Yarn in another data center, right? So this decoupling between and your data sources kind of exist everywhere, right? So this decoupling between what your ingest jobs are, how they run, what's the logic, and the execution engine in which they finally execute is kind of actually a practically useful thing to have. And operationally also, if you're doing a lot of Spark, then why not consolidate your data ingestion jobs also, fold them into Spark, so you'll be looking at the same log files and whatnot, and so that's like practical benefits, right? And most importantly, Spark fundamentally differs from MR in the sense that Spark is a general DAG engine, unlike MapReduce, where there is like just like two layers, right? There's a map stage and a reduce stage. So if bringing something like Spark can actually open up the doors for more additional stages in your ingestion job, like you may want to filter something before you load it in, and you may want to do some shuffles or whatnot, right? Maybe you want to like produce like another pre-materialized hive table that you want to do in a different way than how it's partitioned in the source, but you get the gist. So I think that's actually the power of bringing Spark into the mix here. And so with this, right, so the remainder of the slides, we're going to go over how we did this, and then like go into how this actually works. Basically go over the stuff that Veena went over for MR, so that we want you to take away that this is how the MR engine works, this is how the Spark engine works, and these are all the differences. So going back to what Veena was mentioning, so we have these 3 steps, even for the Sqoop job that now runs on Spark. So creating the job, the submission, and the execution, right? So let's kind of dive one by one. So what we did was, high level, we realized Spark is a different animal, and you'll realize how as we explain this. So most of our interactions between Sqoop and Spark is like implemented in this class called Sqoop Spark job. And high level, we obtain a Spark context out of it by parsing in all the link configs and so forth. And we pretty much create a driver program and then call Sqoop Spark job.execute, pass in the Spark config with all the job config and the context, and then like submit it high level. So the gory details, right? This is how like a driver program sort of looks like for like a job which reads from JDBC and writes to HDFS, your normal vanilla Sqoop use case, I guess. So line 1, you can see that we're initializing the Spark job. We're taking all the link configs, or like at least which links to load. You can pre-create the links and just pass in the link names to load here. And we create basically line 2 Spark context out of this. Line 3 just sets up the, like as before, the from link, to link, the Sqoop job, the stuff that we saw before when Veena was explaining the MapReduce code. And then we simply call Spark job and execute, and that's pretty much it. This is a driver program, and now basically we have to figure out a way to submit this into Spark, right? I think this is where we hit a lot of roadblocks, because MapReduce has like a very good interface for submitting jobs, getting their status, and so forth. And so how many of you guys have written like a Spark job or like played with Spark? Okay, thanks. So basically, Spark is different in the sense that since it's a general purpose DAG engine, the way you do it is you write your code as if it was some Java, Scala, or Python code, and then you simply submit it either to a cluster, or like you can run it standalone if you want for testing and so forth, right? So we explored a couple of ways to actually do this. First was we thought, okay, let's make the Sqoop server the driver program, and then actually send the parallel tasks across. But then there are like limitations around there can be only one Spark context per JVM, and then like in this mode, if the Spark server crashes, your job dies, which is probably not something we all want. And then we realized, we Googled around and stuff, and we realized Hive on Spark, which is an effort to get Hive, like Spark supported as an engine into Hive, I guess. They're running into the same issues. So someone had written like a remote Spark context and like a client to do this, but their usage pattern was pretty different from what Sqoop server does. They were caching the remote contexts and so forth, but the way Sqoop works is it persists all the job configs and job status and everything. There's a clear separation between the job as you define it, and it just hands it off to an external system for execution, and then you query the external system, say a history server, to get how the job is doing, right? So that didn't work out well. So basically, we then settled on, okay, so we can have a driver program, which basically we pass into like a Spark submit. Like this is like a normal way of how you submit any Spark program, pretty much. And this actually had a benefit for us specifically, which I'll go into a little later. So high level, it's like we just built a Uber jar, which is like gets all the dependencies and the Sqoop and whatnot into like this one fat jar. And then if you look at the submit command, we just submit it with the driver program, submit it to yarn, and then it has a bunch of configs around the from and the to, right? So high level, this can be programmatically submitted using the yarn client. This is actually what the Spark submit command does internally. Or we can, like from the Sqoop server, sort of invoke it, use process builder or some way, right? And we can even generate code for the driver if we want. We haven't done those things in the hope of maybe finding a better way to do this, but high level. So, okay, now, right, what really happens, the meat of it, what really happens when you execute it, and why is this different, or what is the benefit? So, again, so the way, so we already looked at the three things in the connector APIs, right? So we have the partitions. So the connector gives us a list of partitions. That is basically the parallelism that it exposes. All we do is pretty simply just turn it into an RDD inside Spark by simply saying like, partition. And then and then that gives us an RDD. That's a context for executing something parallel. There is a map stage which extracts the records, and then followed by another map stage which basically writes the records and does the load. So high level looks like something like this. So we have a list of partitions from the connector, and then like line 1, we basically do the parallelize and obtain the first RDD. And then we basically do a map on the partition RDD, pass in the extract function. So this is going to parallelly call the extract function on all the partitions that were handed out. We get a bunch of data, which is the extracted data out. And then there's a follow-on map in this stage, which passes to a load function, which is pretty straightforward. So we choose to have these like 2 stages for a reason, like what we saw in the MR example as well. In some cases, if you're positioning something as a generic end-to-end connector, you need to kind of fan in and fan out. So that's why if needed, basically we can adjust this code so that there is an additional 2.5 step where we repartition this before we can pass it into the last load stage. And yeah, okay, so this is the interesting part. We did some micro benchmarks because most of it is pretty much, the benefits here are as you do the communication between these stages now is in memory as Spark RDDs as opposed to writing like temporary files and stuff, which is how MR would work. So, and then in general, there's a speed up from using the Spark execution engine itself, which is built for speed. So we had a table with like 300K records, not very big, but it's also pretty fat in a sense. It has a lot of columns. And then we saw that like there is, Spark continuous is like outperforms MapReduce. And then we saw a little bit of an anomaly with Spark going up as we increase the number of extractors or the parallelism. And we basically tries to down to the fact that this table is using a string column to partition by, and it's actually not uniformly partitioning. So some tasks are taking more time. But in general, you can see that it takes MapReduce way more executors to get to the same time as what Spark would. So in general, if you're running Spark in your infrastructure already, this could be useful. So yeah, so one more micro benchmark with this time with a table which has like very good, decent partitioning, and then maybe a lot more records. So this is pretty flat Spark. So we deliberately actually stuck to like lower data because we can show like really big data, and then this gap is only going to get bigger because if you give Spark more memory, it's not going to like not spill, and then it's going to be faster, right? So as you, but I think there are lots of Spark versus MR workloads out there in the wild, which are like real benchmarks. Maybe you can look at your workload and like see the benefits that you might get. But that's about it. And now going into like what was easy. So actually we kind of proved out, I think, the pluggability of the execution engine because we didn't change a single connector API or any part of the execution APIs, and we are able to add a new execution engine, which is kind of cool. And then in general, some developer love about Spark, the whole inbuilt support for running in standalone or cluster and so forth is like super useful to like, debug and iterate when you're doing this on Spark. And then, as I mentioned before, one of the other reasons why we went with the Spark submit command route is because Sqoop 2, as of now, does not have very good UZI integration, which is needed for running this jobs like periodically. So, but we are able to just create like a UZI action out of this once we define the job and everything, and then like have it running for us. So that kind of served a practical purpose for us. So we went that route. And the things that were not easy, the more interesting part. So most of the time that we spent were actually to figure out a clean way to submit a Spark job, like a submit API that we can later query and get like stats or status or something, right? I think this is like a gap that is currently present, and we are hoping that we can explore something better in the future around this. And then for the most part, we had to convert a bunch of core Sqoop classes to be serializable and whatnot so that Spark can like move them around when it's doing the execution. And this is more tedious than like this. There are probably better ways to do it using Creo, but we haven't explored it, probably something to do. And again, like, so now this project became a melting pot of MR dependencies and Hadoop dependencies, and then Spark brought in its own dependencies. And then so that presented a bunch of interesting Maven like exclusions and whatnot. I'm gonna just hand it over to Veena for the next steps.
Yeah, we don't have much more, but that was pretty much on what we both worked on, porting and running Sqoop jobs on Spark. We have more to do. We just did a POC for a few weeks and ran a few sample jobs and trying to use that and learn from it. There are some steps we want to do next is kind of explore a much cleaner and alternative ways that we could do submission and plug that into getting the job history back easily. Currently, it's not there. So that's something we want to focus on. As I said, we always talked about the transformation part, which is pretty nifty, considering how easily you can chain a bunch of things in Spark to transform data. So we intend to propose this, and this is part of the Apache Sqoop project. So we intend to propose extending the connector APIs to not just to extract, load, and partition, but also a few filtering and transformations that each connector could expose, that the jobs can dynamically pick up, like when it wants to filter based on a regular expression, or filter based on a column, or like massage some sensitive data. These are things that could be plugged in the same stage, because Spark APIs are so easy to chain. And lastly, as I said, we're working with Apache Sqoop. I was part of it. I no longer work in Cloudera, but I think my goal is to kind of work and get feedback from the community and give this back. Currently, the code is in our private repository, in my own private GitHub, but public. You can feel free to check that out. As I said, it was a 2-week POC. We really didn't have to do too much to get this pluggability in and run a few jobs on Spark and get the benchmarks. So that's where we are, and we want to use it at our company and see how it goes. Lastly, I just want to thank a few people, both at Cloudera and Uber, for just allowing us to just run with this and just learn something along the way on how Spark could be used on Sqoop. That's pretty much it. So as was a short, sweet talk, we still have 8 minutes more. I'm happy to take any questions, or you could reach us at our Twitter IDs right there.
Very interesting work. I have a couple of questions. First, have you considered other execution engines, like maybe, for example, Storm, where it has a much more structured job submission tracking kind of interface? And yeah, I'll wait for my second question.
We did talk about it a lot. I think in general, anything that kind of executes a DAG, and if you can separate out your jobs and you can keep moving them between them, it'll be like, between different such execution engines, this is like a separation between infrastructure and business rules, right? So that I think will be useful. For us, we just went with Spark because we do a lot of Spark at Uber. So we just wanted to see if we can consolidate everything into like one infrastructure. That's the motivation for us to try Spark. But you're right. We can take a stab with Storm too. That'll be useful.
Sure. Thanks.
Right. So one of the original reasons.
Repeat the question.
Yeah. So the question is, have you tried any change data capture with Sqoop and Spark? So one of the reasons is for us to start on this is to tailor sharded kind of database log, and then try to see if we can compact it, or this goes along the lines of the Hive talk earlier in the day. We've tried something around it, and then that's when we realized that the intermediate files between the stages was taking a lot more. We wanted to kind of take the change logs and partition it in a different way. So this is actually, the answer is yes, we tried something, but it's not completely there yet. Right, I think it's a very good question. So the question basically is, usually SQL to Hadoop, there is some guarantees around like data duplication, or like how the data is committed into the final destination. So now if you're writing to Kafka and everything, does Sqoop itself provide any kind of data duplication guarantees and so forth? Am I right? Okay. So right now, do you want to take this? It's a
Yeah,
Sqoop
so
question.
basically in MR, there was this output format that they used to finally commit or abort based on the stuff that MR returned, right, based on the success or the failure. So similar thing has to be done, is done in the Spark case, wherein based on the Spark API coming back or not, you either create the final job submission or not. So it is pretty much the same. You don't do anything different in the Spark case. But in terms of data integrity, duplication, it's really hard to manage that from the Sqoop level. Sqoop only manages whether the job succeeded or failed completely. If there were duplicate records written based on how the loader API was implemented, it's up to the connectors at that point of time to handle it. Thank you.
Did you try it around large or medium blobs? Sorry? Medium or large blob data. So did you try it around that?
Blob data for the.
Right, so as I showed, we mostly just micro benchmark, mostly due to the lack of like infrastructure to like kind of test. Our dev cluster only had like so much space, but I would say that largely connector API, I said this is just Spark versus MR. So if Spark can do it, I think the connectors would be able to do it.
Hey, what version of Spark was this tried on?
1.3.1,
Okay.
the latest one. Right.
All right. Thank you, guys.
All right. Thanks a lot, guys.